So this is your study guide for the Unit 6.3 chemical processes. And this is your answer key. So I'm not going to give you an answer key. Um, in order to get the answers for the study guide, you need to watch this video. Otherwise, yeah, good luck on the test. Um, so we're just going to go through these. The first question here is, does the chemical reaction below display an example of the law of conservation of matter? We've got two hydrogen molecules and we've got two oxygen molecules. Okay, so if I go over here and look, I've got two oxygens, right? Two oxygen atoms. Over here, I've got two oxygen atoms. And I've got 1, 2, 3, 4 hydrogen atoms. 1, 2, 3, 4 hydrogen atoms. So does this show the law of conservation of matter? Yes, this shows the law of conservation of matter. Okay, now I need to explain, why does it show it? This shows the law of conservation of matter because there are two water molecules in the reactant side of the reaction with 4 total hydrogen atoms and 2 total oxygen atoms. Period. On the product side, there are 2 hydrogen molecules with a total of 4 hydrogen atoms and 1 oxygen molecule with a total of 2 oxygen atoms. There are no new atoms added to the product side, and there are no atoms missing from the product side that began on the reactant side. Period. You know, it's a lot of information, okay, but there you go. All right. So there's your answer to number 1. Okay. There's our answer to number 1. Look at that. All right. So now we've got question number 2. This one's actually kind of a fairly easy answer. Describe why food is important to an organism. Food is important to an organism because it gives nutrients and energy to the organism. And it's as simple as that, you guys. This one's not a terribly difficult answer. That's a pretty straightforward question right there. Okay. So question number 3, iron on cars and bikes reacts with oxygen to form iron oxide, also known as rust. Okay, so here we've got our reactants. Right here we've got our reactants. Okay, and we've got our product. Okay, we've got our products. So reactants, these are the chemicals that come together. Products are what we have left over. So iron and oxygen combine together to make iron oxide. Okay, so it says Describe the properties of the products versus the reactants. Okay, how are they similar or different, and why is this the case? So we've got iron and oxygen. Says we need to compare iron and oxygen, right, our reactants, to our product, iron oxide. All right, so iron, okay, we're looking, okay, it's gray in color, oxygen is colorless, and it makes a reddish brown color. Okay, so we could say that, you know, um, similarities are iron and iron oxide both have color. Okay, they do not dissolve in water. And let's see, they do dissolve in water and are both solids. Okay. And then we'll do the differences. Differences are they are different colors, have different densities, oxygen and iron oxide have different states of matter. Excuse me. So there we go. All right. So it says earlier in this unit, you took an Alka-Seltzer tablet, added it to a beaker, and added water. You weighed the beaker, Alka-Seltzer tablet, and water at the beginning and the end. You observed bubbling and concluded a chemical reaction occurred. Is it correct that a chemical reaction has occurred? Describe why or why not. So think back to that lab. Did a chemical reaction occur? Yes. A chemical reaction occurred. Why? The Alka-Seltzer reacted with the water, creating a gas. Okay. I mean that's as simple as that. The Alka-Seltzer reacted with the water, creating a gas. No mass was lost thanks to the Ziploc bag, which contained a reaction. There we go. Okay. Okay. Was the boundary a system? Okay. Was the boundary a system? Was the Ziploc bag containing the system? Yes. Right? Yes. The boundary. What's the boundary of the system? Let me read this again. You observed bubbling and concluded a chemical reaction occurred. Okay, yeah. Yes. The boundary. What was the boundary? Sorry. Man, I did not read that correctly at all. What was the boundary of the system? The boundary system was the Ziploc bag, which held in the reaction, as we already discussed. Right? We already said that. All right, so if the Alka-Seltzer tablet had been placed in a plastic baggie with water and sealed, would the mass have changed? Well, that was part of our reaction. Did the mass change in our Alka-Seltzer experiment? No. Right? No. The mass would not have changed. Right? The Ziploc bag held in all of the reaction. The mass of the tablet was changed to the gas in the bag. And there you go. I mean, it's really fairly simple, right? The mass that we had for the tablet just got changed into the gas that was in the bag. It's really that simple. All right. All right, so now we got another problem here. Lithium and water react to make hydrogen gas and lithium hydroxide, according to the reaction below. So we have lithium plus water creates hydrogen gas plus lithium hydroxide. To form lithium hydroxide, each lithium atom bonds with a certain number of hydroxide, or OH, molecules. The model below shows the reactants, lithium and water, but the products are incomplete. So a hydroxide molecule is made up of one oxygen atom bonded to one hydrogen atom, like this. So we've got oxygen and hydrogen, just like this. So it's asking us to complete the model. So if I'm looking, right, so if I were to scroll all the way back up here to question number 1, right, how did we figure out that this was the law of conservation of matter? We just counted the number of atoms on each side, right? This arrow is kind of like an equal sign. I'm just counting the number of atoms on each side. So if I go back down here, right, all I'm going to do is I'm going to count the atoms. So I've got 2 lithium atoms over here. There's my arrow, my equal sign. And look at that, I got 2 lithium atoms over here. Perfect, right? Those are right. So I know I don't need any more lithiums. So if I look at water, I've got 2 oxygens. I'm missing 2 oxygens over here. I'm probably going to put an oxygen on both. I'm probably going to have an oxygen for each one. Okay, let's look. I got 1, 2, 3, 4 hydrogens. Yep, 1, 2. So I know I've got to have a hydrogen for both. So each one of these lithiums is going to have one of these molecules, right? So let's see if I can do this here. Let's see if my yeah, it's not going to let me. All right, so you guys are just going to bear with me as I keep editing this. Okay, but each one of these lithiums is going to have an OH next to it. And then just count it up and make sure you got the same amount of each type of atom on each side of the arrow, and you're good to go. Describe how we decided to do this. What do you think it was? Well, the law of conservation of matter states that matter cannot be created or destroyed. Right? This means that all of the atoms we started with must be present at the end. It's as simple as that, you guys. I'm not really looking for overly complicated answers. It's really that simple right there. That answer right there. Boom. The law of conservation of matter. Right? That's all it is. Okay, so let's look at this next one then. Okay, so let's look at number 5. So it says, consider the following chemical reaction for elephant toothpaste. And hydrogen peroxide becomes water and oxygen gas. So it says the number and types of atoms are the same in the reactants as the products. Are the properties of the reactants likely to be different from those of the products? Why or why not? So is hydrogen peroxide, are the properties of hydrogen peroxide different from the properties of water and oxygen gas? What do you think? What do you think? Do you think they're different or the same? Well, I hope you said they're different because they're different, right? The properties of hydrogen peroxide are different. The properties of hydrogen peroxide are different from the properties of water oxygen. And now why? Why is it different? What makes the properties of hydrogen peroxide different from the properties of water and oxygen? They are different because they are different substances that have different amounts of atoms, right? They have different amounts of atoms, right? This is H2O2, and this is H2O, and then this is O2, right? They're different. They have different amounts of atoms. They're not the same. But like a very simple answer right there. They're not the same. They can't be the same. They can't have the same properties. They're different. They're different altogether. All right, let's look at this one. Many foods that we eat contain proteins. Proteins are large molecules made of connected amino acids. The model below shows how proteins are broken down through chemical reactions in different phases of digestion. Each square represents one unit or one sugar. So I think we did something similar to this. If you guys check your notes, I guarantee you have something similar to this. You have a packet that kind of we went through this. Okay, so protein in the food, as we chew it up in our mouth, these proteins are going to get broken down, and it's going to go from having 1, 2, 3, 4, 5, 6, 7, 8. It's going to go from being one string of 8 to being 2 strings of 4. And then in our stomach, it goes to being 4 strings of 2. And then in the small intestine, what do you think it's going to be? Well, it's going to be 8 individual squares. And I hope you've drawn all of those, right? So we go 1 string of 8 to 2 strings of 4 to 4 strings of 2 to 8 individual squares. Why did we draw our picture this way? Because at each stage, chemical reactions, not even chemical reactions, um, processes occur that break down the food into smaller pieces. And that's it. It's that simple, you guys. It's really that simple. Not terribly difficult. All right. Sorry. Number 7. When Yeti was developing their coffee cups, they were seeking to make a cup that could keep the liquid inside of it holding its temperature for the longest time. Several different materials were tested. Engineers worked on various designs for cups by testing different combinations of substances. To test each design, the engineer measures the temperature change of a sample of heated water. Example results of these tests are shown in the figure. Okay, so this is the figure right here. So what makes each design the best solution? So design one is this dashed one right here on my screen. It's blue. On your paper, it's going to be probably a darker gray color. So what makes it the best design? Okay, I would say what makes it the best design? It stays warm. It stays hot for what would we say, 7 minutes before cooling. Okay, what about design 2? What makes design 2 the best? Design 2 is this one right here. This one that's red on my screen. It's probably a lighter gray like a little bit lighter gray on yours than what the blue one was. What makes it the best? It cools quickly. Right? Maybe we want a mug that cools our drink quickly, but then kind of stays the same for a long period of time. I don't know. I don't really like drinking hot stuff. I like stuff that's like warmer than warm, but like I don't want stuff scalding my mouth when I drink it, Right? And then design 3, it's this really light one right here that kind of consistently goes down, right? It takes the longest to cool. Right? So each design really does have something about it that makes it really good. So if we're looking, right, if the solutions are compared using the criteria of slowest temperature decrease after 30 minutes, which solution is the best? Well, if we look at our graph, right, which one, all the way here at the end, which one had the lowest amount of cooling? Well, it'd be design 3. So design 3 would be the best, right? Design 3. Design 3 would be the best. Right, so one company that sells Yeti requires that the design meet several constraints, including that the sample of water must cool no greater than 25 degrees and must gradually cool continuously even after 10 minutes. So it can't cool more than 25 degrees. So that eliminates design 2, right? Because design 2 comes down here like below 70 degrees. So that means it went down 30 degrees. And then let's see, it must gradually cool continuously even after 10 minutes. So let's look at 10 minutes. Well, that eliminates design 1 because design 1 doesn't, it's going down really fast after 10 minutes. Whereas, here, so design 3 again has to be the best, right? Design 3. So if I'm the Yeti company, I'm going for design 3 a whole bunch. Design 3 would be my go-to. All right, so this last one says magnesium is the main substance contained in one design for a self-heating meal. If you mix magnesium powder with water, you would observe that heat is produced. After several minutes, no more heat is produced and a powdered solid remains. The properties of these materials are shown in the table. So when magnesium oxide was combined with water, what type of change occurred? Okay, what do you think? If I throw magnesium into water and it starts to heat the water, we know there's a release of heat, which means that there has to be a reaction that occurred. It's not a physical reaction because there's no such thing as a physical reaction. It's just it's a physical. Oh my gosh, I totally blanked on the word at the moment. Okay, but it's not a physical reaction. Oh my gosh, I cannot think of it. But we know it's not a physical. It has to be a chemical, right? It has to be a chemical. Heat is being produced, which means that atoms and molecules are being broken down because they're releasing heat. It's got to be a chemical reaction. Okay. How do we know? Heat is being released, indicating chemical reaction. Okay. And there's your answer right there. Okay. It's that easy. Now, this will be posted on Google Classroom for you tomorrow. So if you missed anything, you're welcome to go back in this video and check it. Otherwise, just go check Google Classroom. The answer key will be on there after, within about 10 minutes after this video is posted. All right. If you have any questions, you can always email me. Just email me. I probably won't be able to email you till Saturday, but if you have a question, just let me know. All right. Good luck.